So welcome everyone. Welcome back for the last talk of today, and that's by Helena Lopez from Rio de Janeiro, and she'll be talking about the 2D incompressible ideal flow. Helena, over to you. I might sort of tell you when it's about 50 minutes up or something like that. So, you know.
Yeah.
Over to you, Helena.
Just one moment. I need to do this. Okay. All right. So first of all, I want to thank you very much for the invitation to speak here. It's a real pleasure. It's a real pleasure to do this. Hello? Yes. It's a real pleasure to give this talk to you. I'm going to be talking about necessary and sufficient conditions for energy balance in 2D incompressible ideal fluid flow. And I'd like to start by acknowledging some collaborators. So there's going to be basically, this is based on 3 pieces of work. One is by, is joint with Alexei Sheskinov and Roman Shvidkoy and Milton Lopez-Filho. The other one is joint with Fabienne Jin, Samuel and Haller, Milton Lopez-Filho, Siddhartha Mishra. And then the third one is by Milton Lopez-Filho and myself, just with Milton. Okay, so the equations modeling unforced incompressible fluid flow are given by UT plus U grad U is minus gradient pressure plus nu Laplacian U, and divergence of U is 0. And nu equals 0 corresponds to the Euler equations, which are a model for ideal and viscid fluid flow. And nu positive corresponds to Navier-Stokes equations, which are a model for viscous flow. So for smooth solutions, we have ddt of 1/2 of U squared, which is the kinetic energy because the density is set to 1. This is equal to minus the integral of U times U dot grad U minus the integral of U times gradient of pressure plus nu times U Laplacian U, just by multiplying our equations by U. We're taking the inner product with U. And using the divergence-free condition, you can rewrite this as a sum of divergence of exact derivatives, divergence terms, minus nu times the integral of the gradient of U squared, which is simply minus nu times the gradient of U squared if you don't have any boundaries. Okay. Oh, I'm sorry. In all cases, if U satisfies either no slip or just the non-penetration condition. So if you have smooth inviscid flows, in other words, nu equals 0, energy is conserved. Okay. And however, anomalous dissipation is a cornerstone of turbulence theory, and inviscid fluid flows, these correspond to inviscid fluid flows which do not conserve energy and which are limits of vanish of viscosity. So the dissipation rate does not vanish when the viscosity tends to 0. So turbulence needs a, and what we've just seen is that means that we have to consider irregular flows. So I recall the Anzara conjecture from 1949, which says that anomalous dissipation may occur in inviscid fluid flow with less than 1/3 regularity, but if the inviscid flows are more than 1/3 regular, then they necessarily conserve energy. And as we know, research developed along 2 fronts, the flexibility front and the rigidity front. And last week, we discussed the flexibility side and the method of convex integrations, which led to wild solutions. Today, we are going to concentrate on 2-dimensional flows.
Can I ask you interfere? I'm sorry to interfere. Can I ask a question, please?
Sure.
In turbulence, you say for conservation of energy.
I can't hear you.
In turbulence, for conservation of energy, you are assuming that there is no other form of dissipation other than molecular or viscous.
Yes, unforced flow.
Unforced flow, that is right. But there can be pressure diffusion, diffusion in the form of waves, acoustic energy. So that is neglected.
Yes, I'm assuming we're doing just Navier-Stokes, just pure Navier-Stokes, no acoustic waves.
No, it is Navier-Stokes, but it is compressible, isn't it? You are considering incompressible. Even in the incompressible limit, I mean, at the small scales, I mean, I don't know how you can consider it as completely incompressible at the small scales. I mean, you may say it is incompressible, but it is not in incompressibility will not exist all over the region. Yes, see, that is not.
Okay, so I'm
So
assuming mathematically, this is as everything. This is always a sort of an idealized model. Okay.
There is a
So
pressure.
I'm throwing away everything else.
Yeah.
This is just pure incompressible Navier-Stokes. Actually, it's pure incompressible Euler, and I'm going to look at 2D flows. Okay, so I'm looking at the 2D Euler equations on the torus with no other effects, with initial data in L2. And here I put the most general form, which has forcing F, okay? And I'm going to start this talk by discussing weak solutions for which the vorticity is pth power integrable, okay? And I will also start this talk by looking at flows without forcing, so F is 0. Later on in the talk, I'm going to address the case of forcing, which is the main point of this talk. So note, smooth vorticity is transported in 2D, so LP bounds are preserved by the evolution. LP bounds meaning the integral of the pth power of the vorticity. And wild solutions have no control on integrability of vorticity. So I'm going to be contrasting the situation with wild solutions. Okay, and that's true even in the scenario that was discussed by Liabrué and Maria Colombo, for which the vorticity was in L1 infinity. L1 infinity is weak L1. That means that the distribution function of the vorticity satisfies an estimate. It's under control, but that's it. Okay, so there's no integrability. So let me start by giving you a definition of a weak solution in this scenario, in this context. So I fix a finite time horizon and initial velocity with finite kinetic energy on the torus, such that the initial vorticity is pth power integrable for some p greater than or equal to 1. Okay, then I say that U is a weak solution if it lives in the space continuous in time into weak L2 with a weak topology, with a vorticity which is bounded in time into LP. If the following identity is satisfied for every test vector field, which is smooth in time into the torus, and such that the divergence of phi is 0. Okay, I forgot to mention it has to be compactly supported from 0 in 0t. So it's 0 at the finite time horizon capital T. So this is what you get if you just multiply the Euler equations or take the inner product with phi and shove all of the derivatives onto phi. Okay, and additionally, for almost every time, the divergence-free condition is satisfied in the sense of distributions. So existence of this kind of weak solutions is known way back since 1987. That was due to Depert and Maida at the case p greater than 1. Then Vecchier-Wood proved this at the case p equals 1 using some ideas developed by Delors in his work on radon measures on vortex sheets. Uniqueness is open except for L infinity vorticity and near L infinity vorticity. I don't want to discuss how near because it gets rather technical. Okay, so we call a weak solution conservative if the L2 norm of the velocity is constant in time, or if the kinetic energy is conserved. It's the same thing. Okay, so let me start with a baseline result. Namely, if I fix a finite time horizon and a weak solution, whose vorticity belongs to L infinity in time, L3 halves in space, then such a weak solution is always conservative. With no regards to how it was obtained, if it's a weak solution, it will be conserved. Moreover, the local energy balance law also holds in the sense of distributions. Okay. So this result is actually it's a corollary, a consequence of the work by Sheskinov Konstantin, Friedlander, and Schmidtkoy from 2008. However, because L infinity, because the velocity will then be bounded in time to W13 halves, the Sobolev space, and that's contained in L3 in time, B1/3 3C0, which is where they prove energy conservation. Still, it's going to be very illustrative to outline an elementary proof. So here's the idea of the proof. I take a mollifier, I take the convolution of the Euler equations with the mollifier, and I write U epsilon to be the smoothed out velocity, P epsilon to be the smoothed out pressure. So this smoothing out is kind of like a low pass filter. So the smoothed out velocity and pressure satisfy this new equation with all of the error term dumped into R epsilon, the Reynolds stress, which is the commutator between smoothing out the velocity and smoothing out the nonlinear term. So if I multiply this equation by U epsilon, I get my local energy balance law, except with the error term, U epsilon dot R epsilon. When epsilon goes to 0, we have ddt of the temporal derivative. Okay, so here we have ddt of U epsilon squared over 2. I want to take epsilon to 0. I have this term, I want to take epsilon to 0, and I have this term, and I want to take epsilon to 0. So the first term will converge to the correct thing in the sense of distributions, the second term as well, and the third term, the error term, converges to 0 strongly in L infinity in time to L1. Now, A and B are actually subcritical for vorticity in L3 halves. You can get much closer to L1. You can go all the way up to 6/5. However, the error term, C, requires omega and L3 halves. Okay, so good behavior of the energy flux term is the key point in all of the results along these lines, along the rigidity line. So the proof of C uses the convergence of the mollifications together with the Sobolev embedding, which says that if the vorticity is L3 halves, that the velocity is in L6, and then Holder's inequality. It's very, very simple. It's elementary. The key fact here is that this term U dot grad U belongs to L1, and the L1 norm is kind of like W13 halves to the power 3. Furthermore, P equals 3 halves is optimal. It's not only a technicality, but it's actually sharp for this method. So we proved with Alexei and Roman and Milton Lopsfiliu, it's an old paper back from 2016, that there exists a divergence-free vector field, which is B1/3 3 infinity intersect W1P for every P less than 3 halves, and for which the flux term does not vanish. This error term does not vanish. Okay, so what is this pi q? Well, first of all, the SQ is a little Wood-Paley truncation at level 2 to the q, and pi q is the energy flux up to wave number 2 to the q. Note, this divergence-free vector field that we build, it's not a dynamical example. It's an illustration that the method that we're using hit a wall. Okay, so it's not a solution of the Euler equations. However, if we look at Kreisman's 2D turbulence theory, we see that it postulates a forward entropy cascade in 2D. And that corresponds to some kind of regularizing effect in 2D. So Kreisman 2D turbulence theory suggests that there may exist a dynamical mechanism which prevents anomalous dissipation in 2 dimensions, even for supercritical flows. And then we will look at vanishing viscosity solutions, which allow supercritical energy preserving flows. So before I get into that, let me note that when I talk about supercritical, subcritical, Onsager critical, there's a formal quote definition of this. The energy flux scales like U times U over L times L to the power n, and it's a dimension of the physical space, times time, and that's U cubed L to the n minus 1 t. So because of the scaling, Ramanujan introduced the Onsager critical spaces, whose definition is B is an Onsager critical if the B norm to the power 3 scales like U cubed L to the n minus 1 times T. So examples of Onsager critical spaces in 3D, L3 in time to L9/5 in space. This is for velocity. L3 in time into H5/6. In 2D, L3 in time into L6. L3 in time into W1/3/2. And in any dimension, L3 in time into W1/3, 3, and L3 in time into W1/3 into B1/3, 3p for any p between 1 and infinity. These three spaces in boxes are spaces on which we actually have proofs of energy conservation. The last one should be p less than infinity here. Okay, so let me discuss vanishing viscosity solutions. So here's a definition. I will take a velocity which is continuous in time into L2, and I will say that it's a physically realizable weak solution of the incompressible 2D Euler equations if the following conditions hold. 1, it's a weak solution. 2, it's attainable as a limit of solutions of the Navier-Stokes equations with vanishing viscosity, attainable in the weak star limit in L infinity in time L2. The initial data converges strongly in L2. Okay, so this is a vanishing viscosity solution or a physically realizable solution. The family, each family you knew, which converges to the weak solution, is called a physical realization of U. Okay, so with this notion, together with Alexei Milton-Lopes-Filou and Roman Schvidtkoy back in 2016, we proved that a physically realizable weak solution for which the vorticity initially belongs to LP for some p greater than 1, or is pth power integrable for some p greater than 1, then it will conserve energy. And I want to note that p between 1 and 3/2 is Onsager supercritical. Okay. So I will discuss the proof very briefly. We start by assuming that the initial vorticity is in LP for some p less than 2, and that it doesn't belong to L2, because if it belongs to L2, in particular on the torus, it will belong to L3/2, and we already know that the weak solution is conservative. Since U is assumed to be physically realizable, we can find a physical realization. In other words, a family of solutions of Navier-Stokes with viscosity nu and initial vorticity omega naught nu bounded in LP, and such that the velocities converge weak star to U, and the initial data converges strongly. If I denote the vorticity for the viscous solutions by omega nu, then the vorticity satisfy the vorticity equation because I'm on the torus, so there's no boundary problems, no boundary layer problems. So dt omega nu plus u dot grad omega nu is nu Laplacian omega nu. And this is a scalar equation because omega nu, the curl of u nu in 2D, is identified with the scalar, which is grad perp dotted with u nu. So if we use energy methods for this equation, plus the Gallardo-Nuremberg inequality and the maximum principle for the LP norm of the vorticity, we obtain the following differential inequality. In other words, if y is the L2 norm squared of omega nu, and C0 is the omega naught nu LP, this is bounded by some constant, then my differential inequality is y prime less than or equal to minus a constant times nu times y to the 2/2 minus p. And the relevant fact is that this power on my right-hand side is greater than 2. Integrating in time and putting back y of t is omega nu L2 squared, I get the following estimate for the L2 norm squared of omega nu at time t. Now, the energy identity for 2D Navier-Stokes is ddt of the L2 norm squared is equal to minus twice the dissipation rate, nu times the L2 norm squared of the gradient of u nu, which I can rewrite in terms of vorticity as minus 2 nu L2 norm squared, the entropy, L2 norm squared of vorticity. If I integrate in time and use the estimate for vorticity, which we just obtained, we get this estimate here. So u nu at time t minus u naught nu, measured the difference in L2 norms is less than or equal to 0, and it's greater than or equal to this right-hand side here. Now, omega naught was assumed not to belong to L2, and omega naught nu was assumed bounded at LP. Therefore, the L2 norm of omega naught nu necessarily tends to plus infinity when nu goes to 0. If it's equal to plus infinity, then we actually get a rate at which these two norms converge to each other, a rate in time and in nu especially. Either way, since p is greater than 1, this exponent here is a positive exponent, as is this one. And therefore, when you send nu to 0, your right-hand side vanishes. And since this is less than or equal to 0, we get that the limit of the difference of L2 norm squareds vanishes. Now, Duprin and Maida in 1987 showed that if the vorticity is in LP for p greater than 1, then the kinetic energy for the Vanacci viscosity limit is equal to the kinetic energy of the weak limit, the Euler solution. So since we assume that we have strong convergence of the initial data, we get that the limit of the kinetic energy of the initial data corresponds to the energy of the initial data for the Euler equation. And therefore, this converges to this converges to this, and therefore the kinetic energy for the Euler solution is equal to the kinetic energy for the initial data for the Euler solution. In other words, we have a conservative weak solution. Okay. In 2021, Samuel and Haller, Sid Mishra, and Carlos Perez Pulido proved the following theorem. They showed that a conservative, physically realizable weak solution is conservative if and only if the Vanacci viscosity limit is strong. In other words, if you have strong convergence of the realization. The key object that they used to do this was the L2 based structure functions. So what are these things? We consider a physically realizable weak solution, a physical realization, and they introduced, this is on Haller, Mishra, and Perez Pulido, they introduced this structure function. So it's the integral on the torus time of the average in a small ball of the discrepancy, u nu at position x plus h minus u nu at position x squared dh dx to the 1/2. They also introduced this other object, which is the time dependent, the averaged in time structure function, where you integrate in time as well. Okay, so recall that phi is a modulus of continuity. If phi is greater or equal to 0, vanishes as r goes to 0. So the theorem proved by Samuel, Sid, and Carlos in 2021 states that if U is a physically realizable weak solution with some initial data with finite kinetic energy on the torus, and U nu is a physical realization, then the following are equivalent. U nu converges strongly to U in LP in time, L2 in space, for some P, doesn't matter which. there exists a modulus of continuity such that the structure function, the time average structure function, is bounded by this modulus of continuity. And 3, U is a conservative weak solution. So they proved that 1 if and only if 2, if and only if 3. In particular, 1 if and only if 3. Let me give you a brief discussion of the proof of their result. First of all, if you assume that U is a conservative weak solution, which is physically realizable, then any physical realization will converge strongly in L2 in time, L2 in space. For any t, we have t times UL2 squared at time lowercase t is equal to the integral from 0 to t of U of s L2 squared, because this is constant, because the L2 norm squared of U is constant, because it's assumed to be conservative. And since we have that the physical realization converges weakly to U, this norm is lower semi-continuous. So this is less than or equal to the limit as nu goes to 0 of the integral from 0 to t of U nu of s L2 squared. Of course, the lim is always less than or equal to the lim sup. And then because we're doing the situation with no forcing, the energy only decreases at the viscous level. So this is less than or equal to t times the U nu at time 0 L2 squared, the lim sup, which is equal to t times U naught L2 squared. Therefore, all of the less than or equal signs are actually equal, and we have convergence of the norms. Convergent now, we already had that the physical realization converged weakly to U. So now we have the norms converging as well, and therefore convergence of norms plus weak convergence implies strong convergence. QED. So that's how you prove that if U is conservative, then the physical realization must converge strongly. Instead of discussing the remaining equivalences, I'm going to just show that if U nu converges strongly, then you have energy conservation. Under the assumption that S2, not S2T, is actually bounded by R to the alpha. Okay, so I'm going to substitute the general case where you have a modulus of continuity by this special case when, without the time integral, S2, the structure function S2, goes like R to the alpha for some alpha between 0 and 1. So we'll show that this implies energy conservation. So assume that S2 of U nu R, which is this the structure function here without for each time fixed, is similar to R to the alpha. Assume that this holds uniformly with respect to nu, and that and uniformly in time. Okay, so then we want to show that this implies, we know that this implies compactness in C of 0 TL2. This is due to the Kolmogorov compactness criterion, plus D2 U nu will be bounded in some negative Sobolev space, plus an Obelian type result. So it remains, so this gives us that U nu will converge strongly in C of 0 T into L2. We were assuming first that it converges strongly LP in time, L2 in space, and we can upgrade this to C of 0 T into L2. It remains to show that the dissipation rate vanishes. So this is based on the following lemma proved by Landhaler, Mishra, Pares Pulido in 2021, that for any vector field which is has two weak derivatives, then the L2 norm of the vorticity is bounded by C times R times the gradient of omega in L2 plus 2 over R S2. With this, we can show we have that if S2 is something like R to the alpha, then you can choose R to optimize this inequality and get that the L2 norm is actually like the gradient of omega nu, L2 raised to this power 1 minus alpha over 2 minus alpha.
Less than 1?
I'm sorry?
Alpha is strictly less than 1 in the...
Yes, yes. That was the assumption. It's an assumption here. This is not the most general case. The most general case is with any modulus of continuity. But this will give you an idea of what's at play here. Okay, so recall the entropy dissipation inequality and input this estimate that we just got, and we get that ddt of the L2 norm squared of the vorticity is bounded by minus c times nu times the L2 norm squared to the power 2 minus alpha over 1 minus alpha. Or in other words, this differential inequality. And this power 2 minus alpha over 1 minus alpha is a power which is strictly greater than 2 as before. And that's what's at play. Okay, just as when we assumed that the vorticity was an LP. So the structure function is playing the role of the vorticity, and the assumption LP is greater than 1 is substituted by S2 being bounded like R to the alpha for some alpha less than 1. Positive but less than 1. Okay. The general case is with a modulus of continuity, and it's a little more complicated. So we integrate the ODE, and as before, we get a power. We get a positive power of nu to pass through the limit. Here, alpha is greater than 0, less than 1 fixed, and we would get a positive power. So we show that the dissipation rate vanishes. And then you conclude as before, compactness in C of 0 to L2 plus a vanishing energy dissipation implies energy conservation. Okay, here are some consequences of this result. Suppose that you have an initial velocity in L2 and an initial vorticity, which is in some space X, which is compactly embedded at H minus 1. Suppose that you have a physically realizable weak solution, U with this initial data, for which the viscous vorticities are bounded in L infinity in X, L infinity in time into X in space. Then any weak limit of U nu is going to be energy conservative. Examples of such spaces X are LP for P greater than 1, and therefore our 2016 result is a direct corollary of the LMPP result. L log L to the alpha for alpha greater than 1/2 is another space which is compactly embedded in H minus 1. And the modified Lorentz space is L1Q for Q less than 2. All of these are rearrangement invariant subspaces of L1, which are compactly embedded in L1, in H minus 1. This was established in an old paper, a very old paper of mine joint with Milton Lopes-Filou and Eitan Tadmor. The proof of the boundedness in general rearrangement invariant spaces of the viscous vorticities, this can be done by operator splitting, and this is part of our new work with Fabian Jin, Milton Lopes-Filou, Samuel Lant-Haller, and Sid Mishra coming up. We have no tools to deal with the initial vorticities in L1 and H minus 1. In fact, the best that we can do is to show that if the initial vorticity is in the modified Lorentz space L1, 2, Q equals 2, it's not going to be compactly embedded in H minus 1, but we can show that the physically realizable weak solution will be conservative. What happens in L1? Or in the space of bounded measures for vortex sheaths, bounded measures intersect H minus 1. So Jean-Marc Delors and Vecchi-Wu, Jean-Marc Delors in 1991, and then subsequently Vecchi-Wu improved this with the L1 case in 1993. They proved that we have no concentrations in vorticity. However, the estimates available cannot exclude concentrations in energy, or in other words, an energy defect. So it is possible. Okay, so that's where we have to look for anomalous dissipation in 2D. Okay, now let me come to the main subject of my talk, which is forced fluid flow and energy balance. So the Euler and Navier-Stokes equations with forcing, I already mentioned before, okay, are here, are given here. Ut plus U grad U is minus gradient of pressure plus nu Laplacian U plus F. Divergence to is 0. And energy balance holds for smooth solutions. In other words, ddt of the kinetic energy is minus the dissipation minus nu integral of gradient U squared plus the integral of F times U. This is the new term which corresponds to the energy input from the forcing. So we seek regularity conditions on F, which lead to energy balanced weak solutions of the Euler equations. Why? Why are we concerned with this? Because low regularity flows are a natural context for turbulence, and forcing is one of the preferred mechanisms to generate small scales. So we want to understand the effect of forcing in all this business. Now we need to adjust our notion of physically realizable weak solutions to the case of forcing. So we have to add the condition that the viscous forces converge weakly to the inviscid forcing, weakly L1 in time, L2 in space. And with this adjustment, in joint work with Milton-Lopes-Filou, we proved in 2021, published last year in 2022, that if a physically realizable weak solution with external forcing, if you have a physically realizable weak solution with an external forcing F, which is an L1 in time, L2 in space, and we have a physical realization U nu with forcing F nu, such that for some P greater than 1, the initial vorticity for the inviscid flow belongs to LP. The initial vorticities for the viscous flows are not only bounded in LP, but they converge strongly in LP. And the curl of the forcing is bounded in L1 in time to LP, intersect L infinity in time at L2. And this condition 3 is a very strong condition. Then U is energy balanced. And this is sort of a first result, a baseline result, if you want. And we were really not satisfied with this. We thought that condition 3 was too strong. Condition 2 is also a bit unwieldy. So in new joint work with Fabian Chin, Samuel and Haller, Milton-Lopes-Filou, and Sid Mishra, we proved this new result, which gives necessary and sufficient conditions on F. So again, we consider a physically realizable weak solution of the incompressible 2D Euler equations with an external forcing F, which is integrable in time at L2, and a physical realization with forcing F nu. So a family of solutions of 2D nu Navier-Stokes or Navier-Stokes viscosity nu with forcing F nu. We assume that both that the family F nu and the forcing F actually are in L2 in time at L2, so they're in the better space. The forcings converge strongly in L2 in time and L2 in space. But notice that there is no more condition on the initial vorticities, the viscous vorticities, and no condition on the curl of the forcing. Everything is done at the level of the velocity. Then U is energy balanced if and only if you have strong convergence of the vanishing viscosity limit in L2 in time, L2 in space. It's a very weak condition for strong convergence. It's not strong convergence at L infinity in time, L2 in the physical space. It's strong convergence L2 in time, L2 in space. So in the remaining time, I will discuss the proof. I have first some observations. First of all, the hypothesis 1, that F nu and F belong to L2 in time L2, is a minimal assumption needed to control the vorticity. Indeed, if you look at the equation for the L2 norm squared of the vorticity, you get -2 times viscosity times the polarentropy, gradient of omega nu L2 squared, plus twice the integral on the torus of omega nu times the curl of F nu. And I can integrate by parts this term because I have no boundary. So I throw this curl onto the vorticity and I get -2 times the integral of F nu times the grad perp of omega nu. And then I can use Young's inequality here and split this integral into a part where I have the gradient of vorticity, which will be absorbed here, and a part with the L2 norm squared of F nu, paying a price which I get a 1 over nu coefficient here. Therefore, if I integrate this in time, I get that omega nu at time t L2 squared is bounded by the L2 squared norm of omega nu at time delta for some positive delta, plus 1 over nu times the integral from delta to t of F nu L2 squared. I also note that even though I'm going to be interested in vorticities for which the L2 norm squared initially is not finite, for any positive time, it will be finite. The other observation that I have is that hypothesis 2 cannot be weakened. Hypothesis 2 was that the viscous forces converge strongly in L2 in time, L2 in space into the inviscid forcing. There is a counterexample given by, if you look at U nu is equal to this object here, you have x perp over x squared. So these are circularly symmetric flows. Sine of x over q root of viscosity times a cutoff in space and a cutoff in time. F nu is, you look at the forcing, which is given by the time derivative of this U nu minus mu times the Laplacian of U nu. Then this new U nu with this forcing satisfies the Navier-Stokes equations because the nonlinear term vanishes. And when you send nu to 0, U nu converges weakly to 0 because of this fast oscillation. And F nu will also converge weakly to 0. So we have that U equals 0, F equals 0 is a physically realizable weak solution, but F nu does not converge strongly to F. And this is not energy balanced. I'm sorry. This is energy balanced, but you don't have strong convergence of U nu to U. Sorry about that. U nu converges weakly to 0, but not strongly. So in the direction U is energy balanced implies strong convergence, you need hypothesis 2. Okay, I will briefly discuss the proof. Step 1, we establish a priori estimates. So this is non-trivial because of the forcing, but it's doable. The energy is bounded, and the L2 norm of the vorticity is bounded by constant over nu times t. So note that even though you lose the estimate at t equals 0, for any positive time, the vorticity has finite entropy. Step 2, energy balance implies strong convergence. So this is the proof. You integrate from 0 to t. You look at the L2 norm in time and in space squared of the inviscid flow, and that's because you're assuming that you have a physical realization. So U nu converges weakly, weak star to U. Then this norm is going to be weakly lower semi-continuous. So this object is less than or equal to the lim inf with respect to nu of the corresponding object for the viscous flows. The lim inf is always less than or equal to the lim sup. And now you use the energy inequality with forcing, which says that the L2 norm squared of the viscous flow is less than or equal to the initial L2 norm squared plus twice the integral from 0 to time s of the integral on the torus of f nu times u nu. And u nu converges weakly to u. F nu was assumed to converge strongly to f. So for each fixed f, s, you have a weak strong pair here, which will converge to the corresponding thing, the corresponding object without the parameter nu. Also, for any s, this object here is bounded. It's a bounded quantity for s less than or equal to capital T. So you can use the dominant convergence theorem or something to say that the lim sup of this is equal to the integral from 0 to t of the initial data, L2 norm squared, the kinetic energy for the inviscid solution, plus twice times this integral here with f times u. And because you assume that u was energy balanced, this object here is equal to the L2 norm squared of u at time s for any s. So you integrate in time and you get the same thing, and therefore all of these less than or equal signs are actually equal signs. And so you have convergence of the L2 in time, L2 in space norms of u nu, and you have weak convergence, and therefore you have strong convergence. So that's how you show that energy balance implies strong convergence. Step 3, strong convergence implies energy balance. This is the heart of the matter. The key lemma is this. If u nu is precompact at L2 in time to L2 in space, and it will be because we're assuming strong convergence, and divergence free, then you can always find a function sigma, which blows up at infinity, so that for any times delta less than t, with delta greater than 0 and t less than the time horizon capital T, the integral in time of the L2 norm squared of vorticity squared times this function sigma of the same integral is less or equal to the integral from delta to t of the gradient of omega nu L2 squared ds. So this is the key estimate that we need, which will allow for that differential inequality, which with a power which is basically 2 plus. This lemma allows us to obtain a differential inequality for y, which is no longer going to be equal. Before, our y was just the L2 norm squared of the viscous vorticity. Now it's going to be the full dissipation. Okay, namely, dy dt is bounded by a constant m, which has embedded in this constant m, there's the initial data for the kinetic energy and the forcing, minus y squared times sigma of y over nu. Okay. So here is our 2 plus power, which then allows us to show that if y nu are increasing functions satisfying this differential inequality, then the lim sup as nu goes to 0 is 0, which is what we want. We want the nu times integral from delta to capital T, the limit when the viscosity vanishes, we want this to be 0. Okay, so we're showing that if you have strong convergence, then you have energy balance. So we already have strong convergence as a hypothesis, and we're showing that the dissipation rate vanishes. We then use continuity in time to show delta can be taken as small as we want. Okay, that's how the proof goes. Of course, this lemma is where we use all the idea of the structure function comes in here. The proof is very similar. It uses a structured function, except that I have simply swept the structure function under the rug. Conclusions. the on-timer scaling is not the last word on inviscid dissipation. There appears to be a dynamical mechanism that avoids anomalous dissipation. At least in 2D, that's the case. Maybe, I don't know in 3D. L infinity W1P, P greater than 1, 2D Euler physically realizable weak solutions conserve energy. This is something that we proved. That's the 2016 paper with Roman and Alexei and Milton in the no forcing case. And this is just an observation that means that these are not attainable through convex integration wild solutions. And maybe this means that you have a selection criteria here. Claude Bartholdi, Dries TT, and Emil Wiedemann had already shown back in 2012 that when they considered shear flows in 3D, that the vanishing viscosity limits select one weak solution among infinite possibilities. Symmetry breaking is another mechanism which is avoided by physically realizable weak solutions. This was proved in joint work with Claude Bartholdi, Mutulopsfilu, Donjoignou, and Dries Titi from 2013. So another instance of a selection criteria here. Okay, so this kind of work, at least without forcing, with vorticity LP, was established for other approximations, namely smooth solutions. In other words, if you have an irregular initial data for Euler, then you can smooth it out. You can generate a smooth approximation and pass through the limit along the smooth approximation. The other method of approximation is weak solutions obtained by the vortex blob method. This is all 2D, which are L infinity into W1P loc for P greater than 1. And local energy balance was shown with forcing for P greater or equal to 6/5. Not 3/2, 6/5. This is work by Gennaro Ciampa, Gianluca Crippa, and Stefano Spirito from 2020. There was one extension to 3D in the case of axisymmetric Euler by Camillo Nobili and Christian Seiss in a paper published last year. They looked at initial vorticity, which is non-negative, such that the norm of x times omega naught is integrable, and omega naught over r belongs to LP in RDRDZ space for P greater than 3/2. And they proved conservation of energy in the case of unforced flows. The remaining question is what happens when P is equal to 1? We have no tools. We already know that there is we don't expect, there's nothing from the a priori estimates which suggests that we will have strong convergence. In this case, we don't expect to have strong convergence, and therefore we don't expect to have energy conservation. However, there's a huge discrepancy in theory, because we know that LP norms of vorticity are conserved all the way up to P equal 1. So a less ambitious program would be to ask ourselves whether, if you take an initial vorticity, which is an L1, and use a physically realizable weak solution, we ask ourselves whether such a U can be attainable by convex integration. And this is work in progress. Thank you for your attention.
Yeah, I would like to make a comment. Yeah, see, even in incompressible Euler flow, there is a pressure term, and the pressure term will definitely lead to pressure fluctuations. And acoustic energy is nothing but pressure fluctuations. So I think the analysis neglects these pressure fluctuations. So it is neglecting some part of the energy which is dissipated in the form of acoustic energy.
In the incompressible case,
I think the problem is you're filtering the pressure terms. You're filtering the pressure fluctuations and neglecting small pressure fluctuations. And that is the reason why the analysis misses pressure diffusion or acoustic energy.
Okay, I think we.
But perhaps you are talking about smooth solutions. Smooth solutions means the pressure fluctuations are filtered.
This is all in incompressible, but let's.
Yeah,
let
incompressible
Elena
flow
answer
also.
this.
I mean,
I think that this
Yeah.
requires some compressibility.
Pardon?
I believe this requires compressibility.
No. I mean, even in incompressible flow, when you go to small scales, I mean, volticity produces a small scales, and those small scales will have pressure fluctuations also.
Okay,
so energy can be dissipated not through just molecular viscous dissipation, but through pressure.
so maybe let's move
pressure
on to
diffusion
another
also.
question, because this was asked before. Are there any other questions? If not, Helena, just one minor sort of, this is from India, one minor technical question and one sort of, if you have a quick remark. So the minor questions in your 2016 proof for the week, so do you have a strong constraint on the modifier you use, or you can just use some C infinity for your psi function or whatever it was for the week?
Okay, just a second. I have to bring back, because I'm not sure what you're referring to. Are you talking about the benchmark result?
Yeah.
The baseline result?
Yes, go back in the very beginning when you were talking about.
Yes.
So there, use a test function which was like a low pass filter, but is that?
Yeah. Okay. No, there's no. Okay, I think you're talking about this. This result?
That's right.
Okay. No, this is just any modifier.
Any modifier. So you don't have a strong, there's C infinity in the torus. And the other is.
Yeah, any smooth modifier, of course.
So the other question is, you said that you're not reporting things for the 3D, but do you have any remarks about these approaches for the 3D Euler case?
No, because we can't do any analysis. There's no estimates. So at least up until now, we don't know how to do anything. We just don't have enough estimates.
Question for.
Hello, so I had a question about which modification of the viscous operator will be needed to actually have anomalous dissipation of energy, because us as physicists, what we know is that there is an inverse cascade of energy, and usually we are using some hypodiffusion or things like that in order to dissipate energy at large scale. So do you think that some of your results could be valid also, or that some kind of operator could lead to some anomalous dissipation of energy at large scales? So some operator acting at large scales.
Okay, that's a very interesting question. I don't know the answer, but this is something I'd like to investigate. I don't know.
Long day, and if there are no further questions, let's thank Helena once again for a very nice set of talks actually in this program. So thank you. Thank you very much.
Thank you for the invitation. Very kind invitation.